Hello everyone, this is ML Naruto. Welcome to my channel. So today I'm going to teach you the implementation part of the linear regression. So in this video, I'll be importing miles per gallon of a car dataset. So here, what I'm going to do is I just simply okay. So I'll be importing the required libraries here. So these are all the required libraries here. So first one is import numpy as np. You all know this. This is a numpy library, numerical Python. Numpy stands for, and this is the pandas library. Import pandas as pd. So I'm just importing this pandas library as in the short form of pd, and numpy in the short form of np. Right. So next, the another library which I want to upload, which I want to import is the matplotlib. So this is the matplotlib library, and I'm assigning it as in the short form of plt. And this particular line, that is percent matplotlib inline, this is the code. This is the line which is useful when we want to plot something and when we want to look at the output. So when you plot something using the matplotlib library, and when you look at the output, that particular output will not be opening inside our Jupyter notebook. That will open uh, out of the Jupyter notebook. Okay, when you tap on that particular output, it will take you to some other, some other place out of this Jupyter notebook, and there you can visualize that particular output. So instead of avoiding that particular thing, so what can I do is I just simply put this particular line, that is percent matplotlib inline. So I'm telling my Python that everything that I plot using this matplotlib library should be should be within this particular Jupyter notebook only. So when I try to visualize the output of any plot using the matplotlib, so I need to visualize it within the Jupyter notebook environment only. So I should not go somewhere else out of this Jupyter notebook. So for that particular thing, I'm using this particular line. And now this is another thing, like import matplotlib.style. So in the matplotlib library, we have some kind of uh, I mean thing called style. So using this particular style, so I'm giving, I want to appear my graphs or my plots as in the style of classic. So for that, I'm using this particular thing. So it is not a mandatory one. You can avoid this or you can just ignore this, or if you want, you can use this as well. Okay. And now at last I want to use Seaborn library. So this is also a visualization library. So I'm just assigning it in the short form of SNS, right? So, and finally, the purpose of uh, our video is nothing but the linear regression model implementation. So for that, I'm importing linear regression model from sklearn.linear model, right? So now when I hit shift enter, what happens? Let's see. So you can see here, it's just running. So it may take a few more seconds to complete the run here. When the star is, when we get rid of this particular star or asterisk symbol, then we can confirm that our particular this particular cell has successfully run. Okay, see, you are observing here lack of star here, so you can confirm that. See here also, uh, so it has successfully been executed. So now what you can do is you can just need to what you can say, you need to read our file, right? So the file is nothing but this particular thing, that is the car underscore mpg dot csv. What does that mean, dot csv? So it means that that particular file is in the form of a csv format file. And you may ask me this, what is meant by a CSV? So CSV is nothing but a comma separated values. So and you may also find that car underscore mpg dot xlsx. That means that particular file is in the format of an Excel workbook. So for now, this particular file has been made in the format of .csv. So for this particular reason, what I'm trying to do is I'm just calling my pandas library, that is pd dot read underscore csv. Why? Because here my file is in the format of .csv. So for that purpose, I'm using pd.read underscore csv. Okay, and now I want to print the first 5 rows. Okay, first 5 rows of the data. See here, if I ignore this, if I eliminate this, what happens? If I hit shift enter, I'll get all the entire data set, that is up to 398 rows and 10 columns it is having, right? So but I don't want to look at this all the rows. I just want to look at some 5 rows. So when you give the function like df.head function, what happens when you hit shift enter? See, you will only get the first 5 rows, that is 1, 2, 3, 4, and 5, right? The rows will start from the index 0 and it will go till 4. Why? Because we are, if you don't mention anything, it will by default takes the first 5 rows, right? For example, if you want to mention something like I want to visualize some 20 rows. So if I give 20 here in the middle of the head function, what happens if I hit shift enter? See, you'll get to know you have got some 20 rows, that is 0 to from 0 to 19 here, right? See, I'm just reducing the screen here, size of the screen. Okay, so by this you can visualize that 0 to till 19. So it is actually giving us the 20, but since I just want you to explain, so I'm not giving the number 20. Instead, I just want you to visualize some first 5 rows, right? Okay, so yeah, so now what can we do here? So now what can we do here? Okay, so just have a look at here. So it is having some 10 columns here. So the first one is MPG and the cylinder, displacement, horsepower, and the weight and acceleration, year, origin, car type, and car name, right? So out of all these, just have a look at here. What do you think? I mean, which column do you think is a complete useless column in our model building? So what do you think? So personally, I mean, when you look at here, so you can confirm that this particular column, that is car name, is of no use. Why? Because see here, there are so many kind of names, but we don't even consider them. Why? Because see, it's actually having Chevrolet and Chevrolet Malibu and some of the Ford Torino, all these things, right? So we don't even consider those cars. What we can do is we can just remove them. So how do you remove any kind of column from a data frame? So you need to use the drop function here. So my data frame is this particular variable, that is df. So for the df, I'm using my drop function, that is df.drop. Inside this, I need to pass that particular column name, which I need to remove. So I want to remove this particular column name, that is the car name, right? So I want to remove this particular car name column. So I'm passing here the car name under the quotes, and comma I'm placing axis equal to 1. So what does this mean? Axis equal to 1 here. So axis equal to 1 means we are saying this is a column, right? When you place 0 in place of 1, so what we are saying is remove the row here, right? But there is no such row, right? With the name car name, right? With the name car name, there is no such kind of row. So I can say I need to remove, since I need to remove the column, so I'm passing axis equal to 1 here, and I need to drop that column permanently. So if I want to remove that column permanently, so what can I do here? I need to put in place equal to true. If you ignore this particular thing, in place equal to true, that won't be dropping. I mean, that particular column won't get dropped for permanently, right? It will just get dropped temporarily. And again, if you run the df, you'll get your column. See, for example, if you want me to show you, see here. Okay, so I'm not telling that Python to drop this particular column permanently. So what happens if I hit shift enter? See, when I hit shift enter, it is giving me the car name, right? So when I hit shift enter, it is giving me the car name. So if you want to drop it permanently, so what can you do is you need to tell Python that I am going to drop this column forever. So in place equal to true. If you provide this and if you hit shift enter, what happens? You won't be getting this car name here, right? See here, the previous data frame has car name, right? And here in this particular new data frame, you don't have any kind of car name here. Did you get that? So that's the thing here. And now you need to have a look at the number of rows and number of columns here. So what are the ways to have a look at the number of rows and columns of a data frame? If you hit just the data frame and if you hit shift enter, you'll observe there are 398 rows and 9 columns here in this particular data frame, right? So this is another way, and there is also some other way. Df dot shape. So by this you get to know that 398 rows and 9 columns are there, right? So this is the thing here. And now, first of all, before building any kind of machine learning model, we need to think that whether these 398 rows are sufficient to capture all the permutations and combinations of 9 columns, which leads to a particular dependent variable, that is NPG. So we need to think that, do we have any sufficient data points to capture the relationship between independent and dependent variable? You need to think before building your model, right? So whether it is the regression or it may be the classification, no matter whatever may be the type of the machine learning model is, you need to think whether these rows are sufficient to capture the information between the independent and dependent variable. You need to think, if for example, if our data has more number of columns and less number of data points, right? So which can't capture all the information, then our model will not perform the production, right? So I'll explain you here with the help of this. Okay, so for example, here you only have 9 columns, right? So the columns are 9, but the rows are 398. Let's assume that these rows are enough to explain the relationship between independent and dependent variable, right? So these rows are enough. Let's imagine this. But what if you have, instead of 9, you have 90 columns here, but you only have some, let's say, 56 rows. So what does this mean? So it means there are not enough data points. Rows are nothing but the data points here. So if you have these 56 data points, so these data points are not enough to explain 90 columns here, right? So this is the thing here. See, for example, here you have so many kind of columns, like for example, 90 columns like this. No, sorry, 9 columns, right? And you have some 398 rows. So which are, let's assume, which are enough to explain, to explain the relationship Okay, so let's assume these 398 rows are enough to explain the relationship between the 9 columns. Okay, I mean all the 8 independent columns and the 1 dependent column. Okay, these 398 rows are enough. Let's imagine this. But what if we have the columns which are some, let's say 99 columns. Okay, but the rows are only 150 rows. So this won't be sufficient, right? So this won't be sufficient to explain the relation between the independent and the dependent column, right? So what happens if you proceed with this particular data? Okay, you didn't bother about this particular thing, and you have processed your data, and finally you have built a linear regression model using this particular data, and what happens, this particular thing won't work in the production environment, right? So our model won't give the best results in the production environment. Why? Because it can't explain the relationship between the independent variables and the dependent variable, right? So this will happen. So for that we need to check whether our data has enough data points to explain the relation between the 8 independent variables and 1 dependent variable or not. We need to check it, right? So now I'm gonna clear it everything. Okay, so now you need to check whether our data has any kind of categorical values or not. If it has any kind of categorical values, then you need to convert that into numerical values, because our algorithm may think that these are the numbers which have values, right? So for example, see here, I'm just scrolling up here. Okay, when you look at here, what did you observe? Actually, what did you observe? See, uh, see here, this particular column, that is the origin. It has the values 1 and 2 and 3. These are actually not a numerical value. These are the labels, right? So 1 represents something like, let's say, Europe, and 2 represents, let's say, US, and 3 represents something, let's say, Asia. So these are just the labels here. So here this is not the case, that is 1 is less than 2 is less than 3. So this is not the case here, this is false here. Why? Because these are the regions, and 1, 2, 3, these are all the labels here. So we need to tell our algorithm that these are not the numerical values, which doesn't have any kind of uh, order, right? So it doesn't have any ascending order, or it doesn't have any descending order. These are just the labels. Okay, every single label is equal. Like 1 is as equal as the 2, and 2 is as equal as the 1, and 1 and 2 are as equal as the 3, right? So we need to tell the algorithm that this is not a numerical value. So for that, what we can do is we can just convert these all the categorical data into some numerical values, right? So you can just convert it. So how to do that, I'll explain you. Okay, so when you look at the particular data here, that is the origin. So here we have 1 represents the America, 2 represents the Europe, 3 represents the Asia here, right? So what you can do is you can just perform one hot encoding, right? So why are we doing actually one hot encoding? See here, df of origin equal to df of origin dot, we are replacing, what we are actually replacing, we are replacing these particular labels with the original values here. So one is a label for America, two is a label for Europe here, three is a label for Asia. So we gonna replace those labels with the original value. So what happens if I do so? See here, our origin column has America in the place of 1, and Europe in the place of 2, and Asia in the place of 3 here, right? So our this particular origin column has been changed right now. So this is nothing but the uh, this is the process of one hot encoding, right? So this can also be called as the dummy encoding. Now, after replacing the labels, that is 1, 2, 3, with the original values of America, Europe, and Asia respectively, then we can perform some dummy encoding or one hot encoding. See df equal to pd dot get dummies. I'm just calling this function get dummies, get underscore dummies. Then I'm passing my data frame, that is df, and I want to apply this one hot encoding on which type of categorical column, that is the columns is equal to origin column, right? So if I hit shift enter, right? So if I hit shift enter, so what happens if you want to check this? See here, you can check it when you call df. So what happens? it again it again has been converted as uh, see here, the column, that is the origin, has been splitted into three additional columns, that is origin America, origin Asia, and origin Europe here, right? So for each of the columns, here we have the values, that is 1 1 1, and here zeros and zeros. So what does that mean? I'll explain. See, when you look at here, so what is the value of origin for the index 0? See here. See, the value of origin for the index 0, what is that? America, right? So in the place of America, what happens is, see, in the place of America, I'll tell you 1 minute. See, in the place of America, for the index 0, it is having some value, that is 1. Why it is having 1? Why? Because here for index 0, the value of America is present, right? So it is having 1. But for the index 0, we don't have any Europe or Asia. So that's why the reason we have the value 0 for Asia and 0 for Europe in the index 0, right? And just now look at the index 1 here. So when you look at here, what is the value of origin for the index 1 here? See here, there is the value of America, that is the origins value for index 1. So Asia would be 0 and Europe will be 0, right? See here, that's what it has happened, 0 0, right? So likewise, it will check with this particular data set. If it is having any value, that value will be considered as 1, and the remaining other two values will be considered as zeros, right? So that will be the case here. Now so okay, you have decided here. So but what is this entire process? This process is known as one hot encoding, or you can call it as dummy encoding, right? So converting a categorical variable into a dummy or any indicator variables, right? So as many columns will be created as distinct values. So what happens when you convert? See here, you have already converted the origin column, which is having multiple categories, that is America, Europe, Asia, into the numeric columns, that is so the origin column has been split into three categories, right? So for example here, see, I'll explain. Earlier, the origin column, right? This is the origin column here. It is only having three subcategories. That is the America, and that is the Europe. The next one is the Asia. So it is having only three subcategories. So that's why the reason three additional columns has been created, right? When we apply this dummy encoding, only three categories have been, three additional columns have been created. But what if we have in the origin column, what if we have one, two, three, and so on? Let's say 300 subcategories, right? 300 subcategories we have like this. So additional 300 columns will be created if we apply this particular get dummies, that is the dummy encoding approach. Additionally, we will get this origin America, origin Asia, origin Europe. Likewise, we'll end up having 300 additional columns, right? So that's what the case here. Okay. So so the disadvantage is that's the thing here. So the disadvantage is you will end up creating whatever maybe the subcategories of a column is. So that many columns will be created, and the advantage is there will be no order among the data set here. So when you apply the dummy encoding here, so America means one, and Europe means two, and Asia means three, but those three are not related to any particular order. That is, those are not in ascending order, or those are not in any descending order. When you apply dummy encoding, so there will be no order among them, right? And this results in the curse of dimensionality. Why? Because you will end up having more number of columns here, right? So you'll end up having more number of columns. So what happens if the columns are actually increasing and the data points are actually very less? So what happens? It may get you your model. This model will not be efficient in the production environment. See here. See, for example, the origin column has, let's say, 300 subcategories here. Okay, 300 subcategories. So likewise, what happens is you will end up creating 300 categories, 300 columns. That is origin America, origin Asia, origin Europe, and so on. Likewise, it will end up 300 additional columns. So then what happens? When you look at here, see, uh, when you look at here, see what is it having? 398 rows, right? So 398 rows and 11 columns, right? So just imagine, just imagine. Uh, so now the columns will be approximately 300. So you end up creating some 300 additional columns, and also we only have 398 rows. So do you think these 398 rows can explain the relationship between 299 columns and one independent? 299 independent columns and one dependent column? Do you think? No. Why? Because we don't have enough kind of data points. For example, if this is, let's say, some 13,980 rows, then you can say that yes, maybe, probably yes, we can capture. Why? Because the rows are very much. The rows are more, right? So, so this is a scenario of the curse of dimensionality, where curse of dimensionality means where we don't have any proper, enough. If we don't have enough data points or rows, no enough data points, but more columns have this, then you can say that this is a situation of curse of dimensionality. You can call it as a curse of dimensionality. So what are the impacts of the curse of dimensionality? Our machine learning model, our ML model will not be working in the production environment. Why? Because it is, I mean, it has failed to capture the information that establishes the relationship between independent and dependent variables. Did you get that? So that's the thing here. Okay. So now, okay. So yeah, you have got the dummies here. And now, what we can do, you can just uh, try to read what the data is actually. So for that, we need to use describe here. So describe dot. So if I use this, see here, I'm getting the entire data with the meaningful information, right? So when you look at this particular data, you can't even understand what's going on within the data. But when you look at here, you will get to know that for each of the column here, the left side, all the name, the left side panel is actually showing you the all the columns of your data set, and the top right here is actually showing you all the meaningful information, that is the count of your individual columns, the mean, the standard deviation, the minimum value, and the 25th percentile, that is the q1, q2, and the q3, and the maximum value here, right? So with which you can understand what's going on within the data. Right. So when you look at the HP column, when you look at above, HP column is actually missing. Although it is having a numerical column, it is actually missing. This means that non-numerical element is there in that particular column, right? So that leads to that is nothing but something we can call it as the data pollution. So due to that, it is not present in our describe input table, right? So for example, see here above, see above. Where is the HP column? This. See, when you look at here, the HP column has 130, 165, 150, 150, 140. So these are all the numerical values, right? But when you look at here, there is no HP column here on the left side. Did you observe? There is no HP column. Why? Because other than the numerical value, there is some kind of non-numerical value involved uh, somewhere within these 398 rows of HP column. So you need to find out what is that particular value which is causing this data pollution. Due to that, HP column is not present over here. So how to do that? You need to understand what are all the data types here that are present in our data. So for that, we have two methods, that is data.info. So by this you can understand what are all the data types. Also we have another method called df.d types here. See, when you type d types here, so what is it showing for HP column? It is showing that it is an object. So it is an object data type. So it is not a numerical, that is, it's not an integer data type, but the HP is an object data type, right? So uh, that is, you can call it as that it has having some kind of string. It can't be used for model building. Why? Because our algorithm only accepts the numerical values of any column, right? So what we can do is we need to find out what is that non-numerical value hidden inside the HP column, right? So uh, you need to find out that. So how to do that? Just do this. We are creating a temporary variable. This is the temp, and I'm saying pd dot data frame. So df dot hp dot str dot each digit. So what I'm saying is this is make this a data frame, and in our data frame df in this particular column, that is the HP column, I want to check whether there is any string involved or not. So if I press Shift Enter, what happens? And I need to print whether there are only non-numerical values or not. So for that, I am using this particular code. That is, in our temporary variable, for this particular column, that is a temp of HP column, I need to know if it is not equal to, I mean, if there are any non-numerical values, then print false here, right? So I'm just see here these values, that is the index 32 and index 126, index 330. These all these rows are having non-numerical values here, right? So all these rows are having the non-numerical values, due to which in the above described plot we haven't got our HP column here. So for that, if you want to know what are those, so what can I do is I'll try to figure out that tail of 50. See here, just go to this particular index, that is the 374 here, right? So just go here and look at this particular HP column. So this is the HP column, this vertical column. So when you go to the to this particular index value, that is 374, and when you look at this thing, this particular thing, this one digit is nothing but the question mark. This is a non-numerical thing, right? And when you look, just go to the 354, right? Where is it? Yes, it is here. So when you observe here, this is also a question mark. This is a non-numerical item. And when you look at here, just go to 336 here. Okay, I don't have any 336. Why? Because I have just called the last 50 digits. So if you check this particular thing, you will find out then all the values, all the index values, all the rows, all these particular rows are having non-numerical elements. That is the question mark. So maybe the person who is actually preparing this particular data set didn't find any value for that particular index, I think. So for this particular column, for that particular row, he didn't find any value, probably. So that's the reason why he has put some question mark over here, right? So now you have got to know that there are some kind of numerical values, sorry, non-numerical values in your data. So what do you do now? You need to replace those non-numerical data with the null values. That is the nan here, right? So nan, what is the full form of a nan? Nan is nothing but not a number, right? So I'm just trying to replace it with the nan value. See, df equal to df dot replace of, I need to replace this particular question mark, that is a string, with the help of an np dot nan. Nan is nothing but not a number. So if I hit shift enter, what happens? So if you want to look whether it has changed or not, see here. Uh, So you want to look for whether it has changed, whether it has applied some kind of changes or not, right? So further, what you can do is uh, you can write this here. Like you are actually checking whether you have any null values in your columns or not. You are actually checking. See, I'm checking here. See, I have null values. Why I am having, where I am having null values? At the row index number 32, 126, 330, 336, 354, 374. See, all these indexes are actually matching with the above non-numerical values, right? So earlier we have already seen these particular indexes are having some question marks, right? So when you check here, when you check here, when you check here, when you check here, all these rows are having question mark here. But when you check here, after applying this, after replacing this question mark with the nan values, you'll get to know that instead of the null values, sorry, instead of the question marks here, I have, I mean, it's clearly visible that there are some nan values. Why? Because we have already replaced it here, right? So that's the reason. And now, okay, you have successfully replaced the question marks with the null values here. But it is not a good method. I mean, it's not a good approach to keep those null values as it is. We need to replace those null values, or we need to fill those null values with some kind of a metric here. So what kind of metrics is really helpful? Like, so you need to think of like df dot hp. So when you think of here, what you can get is in our data frame, inside this particular, for this particular HP column, the median value is some 93.5, right? So you need to replace all these null values with this particular value, that is 93.5. So how to do that? So how do you do that? So using a lambda, you can really, you can really uh, do that. So I'm just applying df dot apply, and inside that I'm placing the lambda here. Why? Because I want to map something. So lambda is used to map something, right? So I'm saying x colon x dot fill in a. So uh, inside this particular x, I want to fill all those not a number, that is all the null values with the help of the x dot median here, right? So when you say that, what happens is it will goes to our data set and it will checks for any kind of null values are there or not. See here, when you look at here, these are all the null values in our data set. So for this particular null values, it will replace all those null values with the help of this particular median, that is 93.5. And I am passing it here axis equal to 0. Why? Because these are all the rows, right? So these are not the columns. These are just the rows here. So that's why I'm passing axis equal to 0. When I hit shift enter, right? Uh, and when you want to look here, and when you look here, like df dot, you need to check right now. See, earlier our HP column has some kind of 1 minute. Okay, so we have already changed the value, right? That is the x dot fill na. With the help, we have already filled all the null values with the help of this median value. But when you try to look at here, what are all the data types involved in our data set? Here, the HP value data set, here the HP column has not been changed. So it should not be in the object type. It should be in the numerical type, whether maybe it should be as float or it should be as int, but it's not the case right now here. So we need to change it, right? So we need to change it. Why? Because our algorithm will not consider the object types in the model building process. So what we can do is, we are telling in our data set, inside this particular for the column HP, I need to change this particular column as float type. So when I hit shift enter, and when I just copy this code, and when I hit shift enter again, so you'll get to know our HP column has been changed to float 64 type. Did you get that? So now when I try to hit when I try to describe, see here, now you will find out this HP column has been included in our describe. Why? Because it is no more a non-numerical value. It is now a numerical value here. It is not a string value here anymore. Why? Because we have already replaced all the string values, that is question mark, with the help of null values. And again, we have filled those null values with the median also. So now you will get to know that HP column has been included in our particular data set, right? Okay. So now what we can do is uh, so you need to have a, pair plot here. So for that, what we can do is I need to create some kind of a temporary another data frame here, right? See, I'm creating some kind of temporary data frame that is df underscore ADTR and equal to df dot ilog. Here I'm saying consider all the columns starting from the 0 to 10, right? So I'm saying consider all the columns here. So how many columns are there? Just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11, right? So I'm saying 0 to 10. That means all the 11 columns will be considered. Okay. And now after that, I need to check what is the output after that. See, I'm just copying. So this, the meaning of this particular code is nothing but I'm just copying everything. I mean, I'm just copying the whole data set, 1 to 10 columns to some duplicate data from that is df underscore ATT. Right? So now I need to draw some pair plot here. See what I can do. So I have taken, I have used Cborn library, and inside the Cborn library, I have called pairplot function. Inside that function, I have passed my data frame that is df underscore ATTR. Now I have used a diagram kind equal to KDE, right? So when you hit shift enter, what happens? Okay, so uh, what is this? What is this KDE here? Kernel density estimation. You can call it as KDE in short form. That's nothing but this particular plot here. You can see here, you can observe the smooth curve here. That is nothing but the kernel density estimation, right? So these are all the smooth curves in your diagonal of the matrix here. So those are nothing but the kernel density estimator here, right? So you need to understand one of the most important technique uh, of a data scientist is to interpret the graphs or interpret the plots here. So when you got, I mean, when you get the plots here, you need to understand what that particular plot is actually trying to convey. So for that, you need to understand it better. Now we are actually, when we are actually doing the regression here, we focus on the diagonal elements, right? And when we are actually doing a classification, we focus on the uh, sorry, when we are doing the regression, we focus on off diagonal elements. Off diagonal means, see, this is the, I'll tell you. See, this is the diagonal elements here, right? So these are these smooth curves are nothing but the diagonal elements here. But when you look at here, these are all the, like, these are all the off diagonal elements here. Okay, so these are all the off diagonal elements. Whenever we do regression, our focus should be on these off diagonal elements, right? But whenever we do classification here, our focus should be on, these diagonal elements here, right? So since we are actually involved in the linear regression, our focus should be having on these, right? Did you get that? Okay. So, okay, what is meant by pair plot here? The pair plot is nothing but a square matrix here. Okay. So the pair plot, how is it actually looking here? It's a square matrix, right? So everything you see below this particular diagonal, that is this part, is nothing but the mirror of this particular part, right? So I'll try to explain with the help of pen here, right? Okay. So this is a diagonal matrix, right? So this is a diagonal elements. So everything that appears that is lying inside this particular diagonals are nothing but the mirror image of what is lying here, right? So you need to study either one thing, either you need to study this or you need to study this part, right? So no matter whatever may be the thing is, there is only this is only nothing but a mirror image of the above one. So I will consider uh, this half, that is this half. So I'll try to read this, I'll try to interpret that particular thing here. Okay. uh First of all, when you look at the first plot, that is mpg versus cylinder here, so what is it actually saying is, see, just look at here, this particular plot here. So what is it actually saying? MPG. So here the plot is between this particular value, that is MPG, and when you slightly look down here, cylinder here, right? So it is saying there is some kind of a negative correlation, right? So there is some kind of a negative correlation involved here. Okay, as the cylinders increasing, the MPG is decreasing. See here, here on the x-axis it is having cylinder, and on the y-axis it is having MPG, right? So what is the trend here? The trend is in the downward direction, right? That is, as the cylinders increase, the MPG, the MPG is decreasing, right? So this is a negative correlation. Negative correlation, it is having the negative correlation, so you can consider it as an important variable. This is an important variable. Why? Because it is actually explaining some kind of relationship between independent and dependent variable. But when you look at here, this is the graph between the what is this, the graph here? Oh, the graph is between the displacement, right? Okay. Okay. So here on the x-axis here, it is the displacement here. On the y-axis, it is as usual MPG. What is the trend here? It is also decreasing. The same. Okay. As the displacement increases, the MPG will always decrease here. And when you look at here, this is also the same here. But what is the value of it here? This is nothing but the horsepower, right? Okay. So this is the horsepower here. So this is the HP and this is as usual MPG. When horsepower is actually increasing, the MPG will always be decreasing here. And this is the weight here. When the weight is actually increasing, the MPG will always be decreasing. And this is the year here. Is that a year? No, that's an acceleration here. Okay, sorry, that's an acceleration here. So this is an acceleration. So it is saying there is no kind of a relationship, right? There is no relationship between acceleration and mpg. Why? Because as the acceleration increases, there are no proper kind of, why? Because this is a pure scatter here. It's not even increasing, it's not even decreasing, it's a pure scatter. So there is no relationship here, right? But when you look at here, this is an year, right? This is an year. When the year is increasing, it is telling that the mpg will always increase when the year increases, right? I'll tell you the logic behind those things. So first of all, look at this particular graph, that is the cylinder here. Okay, so in the cylinder thing, what is it actually showing here? As the cylinder is increasing, the mpg is decreasing. Why? Why does that happening? Why? Because due to the reason, if cylinder increases, the friction in the cylinder increase. When friction in the cylinder increases, it leads to the loss of efficiency, and hence mpg comes down, right? So this is something which is related to a domain knowledge. So you need to have some kind of domain knowledge. Either you can Google or you can ask your client for that domain knowledge, right? Okay, so when you look at this particular displacement here, displacement graph, that is the second graph here, what is it actually explaining here? So when the displacement, what is meant by displacement? Displacement is how far, how far the piston in the engine is pushed in every cycle. As the displacement increases, the friction between the piston and the cycle also increases. If the friction increases, then what happens? mpg will always decrease, right? Okay, so now look at this particular mpg versus acceleration graph here. So this graph, oh sorry, hp versus mpg. So what is it saying is, what is it saying is, when the horsepower is actually increasing, the mpg will always be decreasing. Why? Because we, everybody knows that when the horsepower increases, that is the speed increases, and automatically miles per gallon, that is the mileage will always decrease, right? When you try to increase your horse speed, then what happens? You will definitely lose your miles per gallon speed, right? So this is the weight here. Okay, when the weight increases, the miles per gallon also decreases, right? There is some kind of connection between the weight and the uh, mpg here. When the weight increases on the vehicle, then definitely it will uh, leads to the decrease in the miles per gallon here, right? And when it comes to the acceleration, no matter whatever may be the acceleration is, there will be no effect on the mpg. It is actually saying that thing, right? It doesn't have any correlation between mpg and acceleration, as there is a scatter of data points. It is not an important variable uh, to consider in our machine learning model. Okay, but when you look at the mpg versus year, it has a weak but positive correlation. As the year is increasing, mpg is increasing. That means if a car is manufactured in older year, it will give you the lower mpg. If it is manufactured in the recent years, it will give you the higher mpg. So this is what it's actually saying, right? It's actually trying to convey. So this is the thing related to the pair plot here. Now move on to the next thing here. Okay. Uh, okay. When you look at the diagonal here, okay. See here, when you look at these particular diagonal elements, these diagonal elements here, So what are you actually observing here? There are multiple peaks in some plots. That means there are clusters in our data. So we can perform clustering and see what are those clusters and then decide whatever we need to build. That is whether to build a single model or a multiple models, one each model for each cluster. So we need to decide upon that, right? So, but for the time being, I'm not explaining that right now here. In the future videos, I'll be explaining that. Okay. So, okay, just let's split the data here. Let's split the data. So, how to do that? See, I'm saying that I'm assigning a new variable that is x. See, inside this here, I'm trying to drop mpg column here and x is equal to 1. Why? Because this is a column. That's why I'm placing it as x equal to 1. And uh, I'm saying drop this drop here. What do I need to drop here? Or is in America, or is in Asia, or is in Europe, x is equal to 1. Actually, you can place these columns, but right now I need to explain the linear regression part. So that's why, for making it simple, I'm just trying to drop all these additional columns here. So this I have splitted my data into MPG. MPG column is itself a data frame, and another thing I have dropped the MPG and considered remaining all the independent columns. And here I have only taken MPG columns, right? If I hit shift enter, what happens? Okay, so now from sklearn.model selection, we can test to train test split here. See here, like this. If I hit shift enter, and now what you can do is you need to split the data here on whatever basis you want, like either 60/40 or 80/20, 70/30. For now, I'm taking 70:30. Okay, I'm dividing and saying I want X train, X test, Y train, Y test, and I am using this train test split function here from the model selection library from sklearn. I'm passing all my independent variables, that is X, and dependent variable, that is Y, and I'm saying my test data should be divided in the form of 30%, right? My training data should be 70%, and I'm assigning some random state equal to 1, right? If you assign this random state equal to 1, what happens is every time when you run this thing, you won't have any different kind of values. The data would be split in a appropriate manner, right? So now splitting data into train, okay. Uh, so just try to import the linear regression here. See, I have taken some kind of created one new variable, that is LR equal to I have taken a linear regression function. Now I want to fit that LR dot fit using the X train and Y train data. So what happens if I hit shift enter? See, it has been initiated. The linear regression model has been initiated now. Now I want to know what are all the coefficients involved uh, in my model. So how to do that? So I'm using a small for loop, that is for the index and for the column name. In enumerate function, you need to pass extrain dot columns here. So I'm saying the coefficient of, I'm formatting the text here, that is with the column name. This column name will goes here, and this particular value of the coefficient will goes here, right? If I hit shift enter, what happens? Let's see. I'm getting all the coefficients for each and every single column, that is cylinder, displacement, HP, weight, acceleration here in car type, right? See what happens. See here. just observe here, for the coefficient HP, it is having the negative, right? Negative. But what did you observe here? See, what is this column here? Acceleration. For the acceleration, there is no correlation, right? So there should be zero correlation for the acceleration. But what is it actually saying? For every 1 unit in increase of acceleration, there would be 0.01 times increase in the miles per gallon. It is showing some kind of a positive correlation. But when you observe the plot here it's a scatter. So it's not a positive correlation. But when you try to find the coefficients here, it's showing us some kind of positive correlation. This only happens uh, the coefficient, I mean, it's actually this happens when there is a collinearity in the data, and same with the acceleration column also, right? And same with the displacement column also. When you just look at the displacement here, in the plot here, what is it actually saying? See, where is it? The displacement is here. It is telling you that there is some kind of negative correlation between displacement and mpg, right? But when you look at here, the displacement is some positive, right? So why is it happening? Why? Because the data has some kind of collinearity present in between the variables. So that's the reason here. And now when you try to print the intercept here, so what happens? This is the intercept here. So intercept equal to, I'm creating a variable that is intercept, and I'm telling my model dot interceptor of 0. Okay. So what happens when you try to hit shift enter? You'll get some minus 26.6933. So what is this explaining? What is it actually explaining here? So it's saying when, so this is the x value, right? And this is the y value. So it's saying you will have some kind of x values, right? Like you will have the HP column, and you will have the cylinder column, you will have the displacement column, you will have something like. But we are saying when all our x's are 0, right? We don't have any x's. Then what would be our y value? Either it is 2 or 4 or 26 or what. But here when you look at here, it is showing us when all the x's are 0, it is showing minus 26.693, which is a absolute meaningless, right? Why? Because when all the input variables are 0, how can the value will go up to minus 26.693? There is no meaning in that. So it's a meaningless. So what we can do is we need to scale the data. For that we can use z-score technique later, but for now we can try to find the accuracies of this particular model. So how to do that? So hit shift enter. See here, the accuracies for the training data is 82.5 something, and here the accuracies for the test data is 84. See, the both the accuracies are approximately similar. So this means our model is in the right fit condition. It's not in the underfit or in the overfit scenario. It's in the right fit scenario, right? So that's all for this video, and tomorrow I'll be explaining the entire linear regression process using a stats models library. Okay, so I hope you have got some kind of clarity in the linear regression, as I have been uploading videos continuously regarding the linear regression topic. So I think by the end of this week, I mean, in 2 more days, I'll be finishing this entire linear regression series. The last topics will be regional lasso regression. So by that, we'll be ending this playlist here, and then we'll further move on to the logistic regression. Okay. So okay, I hope I'll see you all in the next video. Take care. Good night. Jai Hind.